Hello, hello. Okay, okay, okay. Yeah, actually, I have the textbook, which looks like this. Okay, so if you like want me to go through the notes, I can do that. Go through the notes first, or we can go straight to the questions. Yeah, or we can go straight to the questions. Up to you, up to you.
Could we do
What
the notes first?
Okay, okay. Yeah. So this is the list of topics, right? Okay. So basically it will cover everything. Yeah. Okay. Um okay. Yeah. So this one later I will send to you. Okay. Yeah. So this one is mostly talking about covalent bonding and then intermolecular forces, things like that. Okay. Yeah. So covalent bonding. Yeah. So because a lot of it is um kind of revision from IGCSE, so I will skip ahead for some things. Okay. So like drawing the dot and cross diagram, you are very familiar, so I will skip that. Okay. Covalent bonding of second row elements. So we are familiar with that because that we learn it in IGCSE. So no problem. So for second row, the maximum number of electrons is 8 electrons. Okay. So maximum it can form 4 bonds. Maximum it can have 8 electrons around. So no problem. So okay, it becomes complicated when we have um third row elements. Okay, so third row elements it can have expanded octet. Okay, what it means by extended octet, because the third row elements they also have the d orbitals. Yeah, okay, so they also have the d orbitals. So 3s 3p and 1 3d. Okay, 5 orbitals. Okay, example, phosphorus. Okay, so which means, okay, so phosphorus is in group 5. Okay, so phosphorus is having 5 valence electron. Okay, 5 valence electron. 1, 2, 3, 4, 5. Okay. So normally phosphorus will bond like this. Okay. With 3 chlorine, in the end, it will have 8 valence electron. Okay. So which is quite normal. Okay. But because um phosphorus is having 15 electrons. Okay. So 15 electrons. 1s2, 2s2, 2p6, and then 3s2. Okay, and then 3p3. Okay, so total 15 electron. Okay, and then it also has 3s, it's like this, 3p like this. Okay, so and then 3d at this moment is empty. Okay, okay, like this. Okay, so now it has 1, 2, 3, 4, 5. Okay, so at this moment it got 3 electrons, but the total capacity is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 orbitals times 2, the total capacity is 18 electrons. Okay, so apart from the 8 valence electron, actually the total capacity is 18. So it can accommodate up to 18. Okay, so that's why for phosphorus it's possible to have this kind of bonding. Okay, so which means, okay, what is actually happening there, instead of forming 3 bonds, it will form 5 bonds. Okay, so instead of like this PCl3, okay, like this, now it is like this. Okay, P, okay, Cl3, PCl5. Okay, something like this. Okay, yeah. So now it got 10. Okay, 1, 2, 3, 4, 5. Yeah. So now it got 10 valence electron. Okay, so no problem. So this one can happen for um period 3, for period 3 elements. Other examples, okay, like sulfur. Okay, so sulfur, it has 6 valence electrons, so it can form SF6. Chlorine, okay, um also in period 3, so it can form ClF3, F5 in addition to ClF, okay? But normally it does not form Cl7, okay? In theory, it can form Cl7, but chlorine is too small for 7 fluorine atoms to assemble around it. So it can have the normal 8 electron, okay? And it can also have this one, uh, basically more than 8 electrons. So this one is also more than 8 electrons. So expanded octet can happen. And then the covalency table. So we can see this part. Okay, so this one is period 1. And then this one, this is all period 2. Okay? No. Okay, until here. Okay, so until here, this is period 2. Okay? And then up to here, okay, so this is period 3. Okay, so for these ones, okay, they can have expanded octet, so they can have uh more than 8 electrons around it. Okay, so aluminum normally does not happen because uh because it's more like a metal, the behavior is more like a metal. So silicon normally no, okay, because it is quite small, okay? But these ones, they can have expanded octet. Okay. Okay, dative bonding is also something new for A levels. Okay, dative bonding, what happened is like this, okay? So this happen normally for things like boron, okay? So boron is so boron, it has 5 electron. Okay, so 5 electron configuration. Okay, 1s2, 2s2, 2p1, like this. Okay, yeah. So it has how many valence electron? It has 3 valence electron. Okay, so 3 valence electron. So it can form 3 bonds. Okay, so it forms 3 bonds. Okay, yeah. So if any time you confuse or not sure, you just stop me, okay, to ask question. Okay, so it can form 3 bonds, but okay, we can see here. So actually it has 4 orbital. So 8 electron max it can accommodate. Now it only has 6 electron, okay, around it. So it has 1 empty orbital that can accommodate 2 more electrons. Okay, so it can happen dative bonding. So it will come from another molecule that has a lone pair. Example, nitrogen has lone pair, so it can bond with BF3 like this to form a dative bonding. Yeah, okay. So dative bond, once formed, it no different from any other covalent bond. Yeah, okay. So once it's formed, we cannot, it basically, it behave like a normal covalent bond. Okay. Yeah. So these are other examples. So this is another example. Okay, so aluminum. Okay, so aluminum, um, if we look at the periodic table, is 10, no, 13 electron. So 1s2, 2s2, 2p6, okay, and then 3s2, 3p1, okay, 13 electrons. Okay, yeah, so we focus on the outer shell, okay, which is like this, okay. So this one outer shell. So aluminum has 3 outer electron. Okay, so it can form 3 bond, AlCl3. Okay, so now it got 6 electrons around it, but 8 max capacity. Okay, so it can receive another 2 electrons. Okay, so example, this chlorine is got 3 lone pairs. So one of the lone pairs can, okay, bond with aluminum as a dative bonding like this. Okay, double, triple bonds. So this is also straightforward, like oxygen. Okay, so oxygen has 6 valence electrons, so it needs to form another 2 bonds to have a full octet. Okay, so it will form double bond, nitrogen will form triple bond, and so on. Okay, so this is mostly IGCSE, so I will just go quickly. Okay, yep. Okay, so another example of the expanded octet will be the SO2, like this. Okay, yep. Third row element can expand their octet. Okay, so now basically sulfur has 10 electrons. Okay, 10
So
outer electrons.
is there like condition that allow the molecule to have this expand octet?
Yes. Okay. Period 3 and above. Period 3. Okay. Yeah, let me open the, okay, periodic table. Yeah. Okay, so in the data booklet, you will have like all the information. So I'm sure you are familiar with this. And then we also have the periodic table. Yeah. Okay. Okay, hold on. Okay. Yeah, periodic table. Okay. So period 1, the max is 2 electron, max capacity. Period 2, 8 electron. Okay. Period 3 is 18, like what I mentioned just now, because it's got the d orbitals. Okay. So we're only looking at outer shell. So for period 1, outer shell is just 1s. Okay. 1s2. Okay. Period 2 is 2s2 and 2p6. Okay. So the max capacity is 8 electrons. Yeah. Okay. So this one we learned in like previous chapter. So if you are not clear later, we can go back also. Okay. So period 3, we have 3s2, 3p6, 3d10. Okay. So like this. Okay. D orbital, we have 5 of them, d orbital. So total 9 orbitals. Okay. Um, each orbital can accommodate 2 electrons. 9 times 2 equals to 18. Okay. So in theory, the max is 18 electron. So period 3 and above, we can have expanded octet. But after that, it's like more complicated. So we don't really need to know that for now. So we just need to know like roughly until here. Okay. Yeah. So max is 18 electron. So like just now we have the okay, yeah. So just now we have the, so this is the table. Okay. Yeah, so we can have this PCl5. Okay. PCl3 is the normal one, which has 8 valence electron. Okay. So PCl5 is having 10 valence electron now. Okay, so 10 electron around the phosphorus is okay because the max is 18. But normally it does not go up to 18 because like this here, okay, like chlorine, um, the max is also 18, but normally it goes up to like Cl3, Cl5, something like that. It does not go up to F7, okay, because there's not enough space to accommodate 7 fluorine. around the chlorine. Okay, but in theory the max is 18, but we can have more than 8. That's all we can say. Expanded octet, it can be 8 until 18, but normally it's like 8, 10, 12, something like that. Okay, normally it rarely goes up to 18. Okay, so the main point is it can be more than 8. Okay, yeah, so if we look at this SO2 example, okay, how does it work? So sulfur is in group 6. So sulfur, okay, electron is 16. So electron configuration 1s2, 2s2, 2p6, okay, 3s2, 3p4. Okay, so this is 16, right? And then 3d0, okay, 3d0, nothing in 0. Okay, so if we look at the valence shell, we have like this. Okay, okay, so p is 3 orbital, d is 5. Okay, so like this, and then 1, 2, 3, 4. Okay, like this. Okay, so it has 6 valence electron. So normally, okay, normally it only form normally it form 2 bonds. Okay, so normally it only form 2 bonds to get the octet. Okay, yeah. Okay, a example, um maybe something like this, SCl2, for example. So sulfur, okay, like this, 1, 2, 3, 4, 5, 6, okay, and then chlorine, like this. Okay, 1, 2, 3, 4, 5, 6, 7, chlorine 7 outer electron. Okay, okay. So in this situation, sulfur, it just formed 2 bonds. Okay, so now the outer electron is just 8. Okay, 8 electrons is the one that we normally have, that we are familiar with. But because it has this, okay, d empty d orbital, so it can actually accommodate more electrons, so it can form this expanded octet. Okay, so now this one, it just take 2 electrons for the reaction, but in this case it will take out 4 electrons for the reaction. Okay, so oxygen, it just 2 bonds. Oxygen, it cannot expand the octet. So oxygen is still 1, 2, 3, 4, 5, 6, 7. Yeah. Okay, I think this is wrong. Okay, this one don't have. Okay, so oxygen is 1, 2, 3, 4, 5, 6, and 8. 1, 2, 3, 4, 5, 6, and 8. So oxygen is period 2. So oxygen, it cannot have expanded octet. Okay, so oxygen is just 2. Okay, but for the sulfur, it can. So instead of take 2 for the uh bonding, it takes 4 for the bonding. So now it end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now it has 10 electrons surrounding it. Okay, so it's okay for sulfur. It's not okay for oxygen. So oxygen is still 8 electron and then 8 electron. So sulfur is 10. Okay, so it can happen for the expanded octet. So yeah, so later when we try the questions, we will see lots of examples. Okay, yeah, so there are also like some more examples here. Later we can try if we have time. Okay, so we can also have odd number of electrons. So this one, it doesn't get asked frequently, so maybe we can just skip ahead. It's just like it has unpaired electron. Yeah. So the unpaired electron, it wants to pair up. Okay. So normally it's more reactive. Okay. So we have other examples that are, we have the unpaired electron, but it can be stable also. Okay, it depends. Okay, next, the shape of the molecules, VSEPR theory. Okay, so this one we never learned in IGCSE. This is new. Okay, so this one, why we want to know the shape of the molecules. Okay, so it's useful to know the shape of the molecules because sometimes the shape of the molecules will affect the chemical reaction. Yeah, okay. So with different shape of molecule, the reactivity will be different. Yeah, so the mechanism will also be different and so on. So it's useful to know the shape of the molecules. And then this VSEPR theory, it give us a method to predict the shape of the molecules. Yeah, okay. So let's say I give you like ammonia, something like that. I give you CO2. Based on our understanding of the VSEPR theory, can we predict the shape of these molecules? Okay, yeah. So the concept of the VSEPR theory is, first, we need to work out how many pair of electrons around the central atom. Yeah, so example, the ammonia, the central atom is nitrogen. Yeah, something like that. For like CO2, the central atom is the carbon. Okay, so we need to work out around the central carbon how many pair of electrons. Yeah, okay. So once we work out how many pair of electrons, the idea of VSEPR theory is that because electrons, they are negatively charged, electrons, they are negatively charged, they will repel. Okay, so they will repel each other, and then when we put this pair of electrons, okay, near to each other, they will repel, they will stay as far as possible. That's the main point. Stay as far as possible for the VSEPR theory. Okay, so yeah, the pairs will take up positions as far apart from one another as possible. Okay, and then from there we can work out the bond angles as well. Some examples. Yeah, okay. So example, let's say this molecule, it got two pair of electron. They will stay as far away as possible. So that will give us a linear molecule with the bond angle of 180 degrees. If three pair of electron, the maximum distance will be like this, okay? Bond angle 120. The shape is trigonal planar. And then four groups of electrons. The furthest distance will be this tetrahedral arrangement, and then the bond angle will be 109.5. And then yeah, so this it is a little bit more complicated, but for A levels we just know a little bit basic like this. Okay, five groups will be trigonal bipyramidal. So bond angle will be here 120, and then here 90. Okay, and then octahedra, six group. Okay, six group will be octahedra, and then all of the bond angle will be 90 degree. Okay, all of them. Yep. And then sometimes not all the electrons, they are bonding electrons. Some of them are lone pairs. Okay, example, nitrogen. Okay, so it got four pair of electrons. Okay, but we got one lone pair. So not all of them are bonding pairs. So these are bonding electrons. Okay, so some are lone pair. Okay, you see the lone pair, you see the electron cloud is bigger, so it take up more space. Okay, so I'm sure you have heard from your teacher like all of this. If I'm going too fast or too slow, if I'm saying something you already know, you can just stop me and skip forward. Okay, yeah, so it will take up more space. Okay, so normally tetrahedral, the bond angle is 109.5. All of them will be 109.5. But when we have the lone pair situation, it will take up more space. So now the bond angle will be less than 109.5. Okay, so the bond angle will be example 107, something like that. Okay. Yes, so the angle between two lone pairs will be larger. Okay, another example when we have water. Okay, so water, it has two lone pairs. Okay, so these two lone pairs, it will take up even more space. Yeah, okay, so even more space. So this one supposed to be 109.5, now it's even less. Okay, this one is 105. Okay, something like that. So lone pair will have the greatest angle, and then lone pair, bonding pair will have a little bit bigger. Bonding pair will be uh uh biggest. Okay, take up the least space. Okay, yeah. So this one example here. Okay, so this one all bonding pair, 4 bonding pair. Okay, 0 lone pair. This one three bonding pair, 1 lone pair, 2 bonding pair, 2 lone pair. Okay, so we can see here this is normal 109.5. Okay, 1 lone pair, it compress. Okay, it compress these bonds here. So now it turned to 107. Okay, when you have 2 lone pairs, it compress even more. So now it's around 104.5. Okay, so that's the idea. Yeah. So here we got other examples like this. Okay, so sometimes we are given like molecules like this. So first we need to work out how many pairs of electrons around, then we can um based on how many pairs we can work out the shape. Okay, so example, this one 4 pairs will be tetrahedral, this one 3 pairs will be trigonal planar, and this one 5 bonding pairs, this will be trigonal bipyramid. Okay, yeah. And then how we consider double bond. Okay, when we have double bond, okay, so this one is 4 electrons, 2 pairs of electron, but we just count this as one group of electron. Okay, we just count it as one group. So that's why CO2 is a linear molecule. Okay, linear molecule. Yeah, okay. Other example here. So sulfur dioxide, okay, you see, we have one lone pair here. So it's supposed to be 120, 120, 120. Because of this lone pair, it compressed a bit. So now it becomes 119. Okay. Yeah. So there are, yeah, okay. So here we got some summaries. Okay. So total electrons, so we need to look at total electron pair, and then we also need to consider how many bonding pair, how many lone pairs, and then we can deduce the shape. Okay, yeah. So okay, so we can go through all of them if you want. At this moment, maybe I just pick some specific example to go through. Yeah, so if later not clear, we can come back. Okay, so example just now, uh we discussed this one. 4 bonding pair, no lone pair, it will be tetrahedral, the CH4 example. Okay, this one, yeah. 3 bonding pair, 1 lone pair, ammonia. Okay, yeah, like this. Okay, so when we're talking about the shape, we don't uh consider the lone pair. We just consider this part. So ammonia, although it got 4 group of electron, it's not tetrahedral. It's not tetrahedral because we don't consider the lone pair. So this one, trigonal pyramidal. Okay, although it got 4 group of electron, but because one of them is lone pair, the shape is trigonal bipyramidal. Okay, and this one, 4 um group of electrons like water. Okay, 1, 2, 3, 4. Okay, so this one supposed to be tetrahedral. No. Okay, because we got 2 lone pair, so we only consider this part. Okay, So we have band. Okay. So not only we need to consider the total electron pairs, we also need to consider how many bonding pair, how many lone pairs. Okay. Yeah. Another example here. Okay. 5 groups of electrons. Yeah, we can see this example here. Okay, 5 pairs of electron. So if we have like all bonding pairs, we will have trigonal bipyramidal. But if we have one lone pair, this one, we have seesaw. Okay, 2 lone pairs. Okay, we have E shape. Okay, 3 lone pairs. Okay, we have linear. Okay, so when we have the 3 lone pairs, the lone pairs will take up this um uh what we call the horizontal position because it will give them more space. They will take up the horizontal position. So the rest will be like this. Okay, so this is linear. Okay, and then yeah, 6 group of electrons, 6 group. When we have all of 6 group, this is octahedral. Okay, 6 bonding, 0 lone pair is octahedral. Okay, 1 lone pair. Okay, what we call this is square base pyramid. Okay, 2 lone pair. Again, the lone pair will take up the bigger space. Okay, which is this 2 here. So we end up with this. Okay, so this is our shape when we have 2 lone pair, which is square planar. Okay, square planar. Yeah, so that's the idea. So I'm going quite quickly because of time. So if anything not clear, you just stop me. Okay, now electronegativity. So yeah. So in the IGCSE, we just learn about the covalent bond, just very basic. Okay, but in A levels, we'll learn about electronegativity because it affects the chemical reaction. Okay, so with some knowledge about electronegativity, we can predict what happened with the chemical reaction. Okay, so it's useful to know. Okay, what is electronegativity? Is um, ability of the atom to attract electrons in the covalent bond. Okay, so let's say we have the CH bond. Okay, CCl bond. Okay, so we form this bond. We have this pair of electrons in between, but this pair of this electron sharing. Okay, so this covalent bond is electron sharing. Okay, this sharing is not always equal. Okay, not always equal, not always 50%, 50%. Okay, why? Because some of them, they have a stronger pull of the electron, some of them. Okay, so how we work out, for example, carbon, chlorine, which one is more electronegative, which one will take up more electron. So example, in this case, it will be chlorine. Example, maybe chlorine will be take 70%, carbon will be 30%. Okay, so we are saying that chlorine is more electronegative, more electronegative. Okay, so later we will discuss why the chlorine is more electronegative. Okay, before that, okay, so in the data booklet, I think this is given. Okay, this information is given. So we don't really need to memorize it. I think it's given. Um, we don't really need to memorize it, but we need to know the trend. Okay, we need to know the trend of the electronegativity. Okay, we need to know the trend, why it is like that. Okay. Oh, don't have. Okay, so the latest version it don't have. Okay, so maybe we need to like pay more attention. Okay, so we can see here this part is low. Okay, this part is high. Okay, so why? The electronegativity will depend on the effective nuclear charge and atomic radius. Okay, so this one we learned in the previous topic, the effective nuclear charge. Okay, so let's say we talk about between lithium and fluorine. Okay, nuclear charge is talking about how many proton. Yeah, how many charge in the nucleus? How many proton? Okay, so if we look at the periodic table, lithium is 3, 4, 5, 6, 7, 8, 9. Okay, so we have the number of proton, how many charge in the nucleus, okay, and the okay, so this is all period 2, okay. So which one will be having like the greatest effective nuclear charge, okay? Which one will be having the highest effective nuclear charge is, okay, so lithium is, okay, the outer electron is 1, okay, Be is 2, okay, and then the B is 3, okay, and then C is 4, okay, okay, N is 5, okay, O is 6, okay, chlorine is, no, fluorine is 7. Okay, which one is having the highest effective nuclear charge? Our answer is fluorine. Why? Because fluorine, it has 9 proton, okay, 9 positive charge to pull on this electron. Lithium is only have 3 proton, 3 positive charge to pull on the electron, okay, because they are on the same period, okay. So this one is shell number 2, okay. Shell number 2, okay, the atomic radius is like almost similar, but the charge is much higher, okay. So we are saying that in this period, the fluorine is having the highest electronegativity. Why? Because it's having the highest effective nuclear charge. Why? Because it got 9 proton, 9 positive charge to pull on the electron. This one only have 3 positive charge to pull on the electron. Okay? Yeah. So we need to understand the trend. Okay? Why like that? Okay. How about when we go from lithium to sodium? It decrease. It decrease. Why? Because lithium, okay, sodium is 11. Okay. So lithium, okay, lithium is like this. Okay. Uh 3 electrons. Okay. Sodium like this. Okay. Yeah. Okay. Sodium got 3 shell. Okay. So can you see the distance? It's much further away. The distance is much further away. Okay. Yeah. Okay. This one is close. Okay. Close to the nucleus. This one is close to the nucleus. This one is far away from the nucleus. So when it's far away from the nucleus, the attraction is less. Okay. So the attraction is less. That's why it decreased again. But going across the period, it increased again. Same reason. The nuclear charge increasing. Okay. But the shell is still in the same shell. It's shell number 3. Okay. This is shell number 2. The distance is almost similar, but the attraction is increasing. Okay. The nuclear charge is increasing. But when you're going down the group, okay, the distance is more far away. Okay. So that's why we need to think about effective nuclear charge and atomic radius. Okay. Yeah. So if anything not clear, you just stop me. So we are saying that fluorine, because it's having more proton, so it got higher effective nuclear charge, example, compared to carbon or lithium. Okay, yeah. So if we have a CF bond, okay, the electron will be attracted more strongly than the to the fluorine. So the electrons will be nearer to fluorine. So that will give us a polar bond. Okay, so this is a new thing for A levels. Okay, we didn't learn in IGCSE. So it looks like this, the polar bond. Yeah, okay. So can you see the electron pair is closer to fluorine, okay? Closer to fluorine because it is more electronegative, okay? So when it's closer to fluorine, it will give us a partial negative charge on the fluorine, partial positive charge on the carbon, okay? So this is what we call a polar bond. And then this symbol here, it tells us the direction of the partial charge. So the partial charge, negative charge is towards the fluorine. Okay, yeah. So, okay, when we're going down a group, so like what I mentioned just now, when we go down the group, electronegativity will decrease. Okay, the outermost is outermost electron is shielded from the increase of nuclear charge and then is further away from the nucleus. Okay, what I mentioned just now, further away from the nucleus. So they experience less nuclear attraction. So electronegativity decreases down a group. Okay, so we need to understand the trend. Why like that? Going down the group will decrease, going across the period will increase. Okay, so we need to understand why. Okay, yeah. So most covalent bonds will be polar, okay? Like CCl, CH, something like that. CO, something like that. So most of them will be polar, okay? Yeah, so we can see this example here. Which one is the most polar? COOH and AlCl, okay? So how can we know the polarity? We find the electronegativity difference, okay? So you see CO, okay, C is 2.5, O is 3.5. So we find the difference, okay? So if we find the difference for all of them, we see that the difference is the greatest for AlCl. So we are saying that AlCl is the most polar, okay? Yeah. So now we're talking about the polar bond. Okay, next we're talking about polar molecule. Okay, so polar bond and polar molecule. Okay, we are not talking about the same thing. Polar bond, we're just talking about the bond itself. Okay, polar molecule is overall the whole molecule. Okay, not the same. Okay, so we can take a look. Polar bond. Okay, we have two types. The bonds. We can have polar bond or non-polar bond. Okay, so what example of non-polar bond like this? HHFF. Okay, like this. OO. So these are all non-polar non-polar bond. Non-polar bond. Why? Because it's pulled by the same thing. They are equally strong. So it's balanced. Okay, so it's balanced. So these are when we have the same thing on both sides, it's always non-polar. Okay, so non-polar bond will always give us non-polar molecule. Okay, so overall the molecule is non-polar. Okay, so non-polar means the electron distributed, okay, evenly, okay, like that. Electron distributed evenly, non-polar molecule, okay. Non-polar molecule, they are normally less reactive. Yeah, so they are normally less reactive. Okay, how about polar bond? Okay, polar bond, we can have two situations, okay. Two situations, it can give us non-polar molecule or polar molecule. Okay, so we'll see why. Okay, You see, this one, HF, is a polar bond. Okay, no problem. And then it's a polar molecule because overall, the electron is concentrated at one side. It's uneven distribution. Okay, uneven distribution of electron. Okay, electron is concentrated on this side. So polar bond, polar molecule, no problem. Okay, this one is polar bond, non-polar molecule. Why? You see, this one we have polar bond here, polar bond, but they cancel out each other. They cancel out each other. So that's why we can have polar bond but non-polar molecule when the molecule is symmetrical. Okay, when the molecule is highly symmetrical, they will cancel out. Okay, when they cancel out, we will get a non-polar molecule. Okay, so for those that are non-symmetrical, we will get polar molecule like this one, polar. Okay, like this one, CCl4. This one also highly symmetrical, polar bond, non-polar molecule. This one, okay, okay, CClH3. Okay, so it's non-symmetrical, non-symmetrical. So we can see the overall dipole is going towards the chlorine because it's more electronegative. Okay, so overall it's going towards the chlorine. So this is polar bond, polar molecule. Okay, yeah. So we need to consider whether the bonds are polar or not. Okay, and whether the molecule is symmetrical or not. Okay, yeah. So this one another example here. So this one will be okay, non-symmetrical. Okay, A and B will be um uh okay, this one will be polar molecules. Okay, this one, okay, it oppose each other equally, so they cancel out. Okay, so we are saying that this one is no dipole moment, this is non-polar. Okay, even if it's got polar bond, it's a non-polar molecule because of the symmetry. Okay, lone pairs and dipoles. Yeah. When we have lone pairs, of course, it's very negative because it got two electrons. So we will have the dipole going towards the lone pair. Again, the dipole going towards the lone pair. Okay, comparing dipoles. Yeah. Okay, so some examples, okay, of the dipole moment of some common molecules. Okay. Yeah, so we can see this HF here, the dipole moment is very strong. Yeah, HF, the dipole moment is very strong. Why? Because this is very highly electronegative, 4.0, okay, 2.1. Very highly electronegative. So it pulls very strongly. Okay, so it has a high dipole moment. Okay, some examples we also have like some less dipole moment. Okay, so we measure using this dBi, okay, dBi this unit, okay. But if we compare to a standard ionic bond is 7 dBi, okay. 7 dBi is still much higher than this, okay. So although these are kind of polar, but compared to ionic bonding, it's still very low, okay. Still a long way from being ionic, okay. But it makes them like more reactive. Okay, it makes them more reactive. Okay. This one, induced polarization of bonds. Okay, so you see this BRBR, BRBR. Okay, normally we are saying that this is non-polar. Okay, because is pulled by the equally strong. Okay, equal to both of them are equally strong. Normally it's non-polar, but sometimes when we have polar, okay, like polar group, okay, next to them, it can induce the polarity. So we can have delta negative here. So it will repel the electron repel to the other side. So now it become polar. Okay, it got the partial charge. Okay, so at first is equally distributed. Now it got the uh, partial charge. So it can happen when we have concentrated electron density next to it, okay, or we have electron deficient atom, okay. You see this ClCl normally should be non-polar, but because we have the delta positive here, it will attract the electron. So now it induce the partial charge, okay. So this is sometimes how the chemical reaction start. Okay, so in general, this is not very reactive because it's non-polar, but because something next to it induced the polarity, now it become reactive. Okay, another example, small highly charged atom near to it. Okay, this one isoelectronic molecules. So this one is just telling us that some molecules, when they have the same number of electrons, they will have the same shape. Like this will be tetrahedral, like this one. They have the same number of electrons. It will give them the same shape. Okay, just like that. Yeah. Okay. Yeah. So this one is talking about sigma bonds and pi bonds. Okay. So this is also we only learn it in the A levels, not in the IGCSE. Okay. So this one we go into more detail how the covalent bonds, okay? How the covalent bonds form, okay? So normally we just know the simple concept, okay? Single bond, okay? And then like double bond, something like that, okay? For IGCSE, we just think like they are the same, this single bond and double bond. But in the A levels, we start to like understand, okay, they are different, okay? So they are different in some ways. Okay. So how well, we have two type of bond, the sigma and the pi bonds. Okay. So we'll see the difference. Okay. So sigma bonds is when we have um direct overlap. Okay. Direct overlap. Okay. Between two orbitals. Okay. This is what we call the head-to-head overlap. Okay. Direct overlap. Yeah, okay. So we can have s orbital and s orbital, example, hydrogen, s orbital and p orbital, example. This one is period one, period one, okay, period one, period two, okay, for example. Okay, yeah, CH, okay, and then p orbital, p orbital. So period two, example, oxygen and fluorine, okay. So this type of bonds, they are normally they are quite strong because the region of overlap is large. Okay, so they overlap directly. Okay, so normally this kind of sigma bonds they are strong. Okay, yeah. Okay, before we go into the pi bonds, we will look at the hybridization of orbitals. Okay, so what means by hybridization of orbital? Okay, let's take a quick look. Okay, electronegativity and tau bonding, we done that. Coordinate and then dot and cross, we done that. Okay, shape of molecule, we done it. Okay, so sigma and pi bonds. So here it does not mention the hybridization. So I'm not sure you want to learn about that or not, but just in case we go through it quickly. Okay, hybridization, because I think it's in the syllabus. Okay, so let's go through quickly. Hybridization of orbitals. Okay, so what are we talking about? Okay, this hybridization of orbitals. Okay, so you see, for the normally most for hybridization, we're talking about the second row elements. Okay, so second row elements, the outer shell, we have the two s orbital and two b orbitals. Okay, two s orbital. Okay, like this. Okay, two p orbitals like this, and then two s orbital is spherical, the shape. Okay, The 2p orbital, they are dumbbell. Okay, so we learned in the previous, okay, we learned in the previous topic already. Okay, okay, like this. Okay, spherical and dumbbell, and then the dumbbell is kind of like, okay, it's kind of like this. Okay, yeah. Okay, so 90 degrees, okay, 90 degrees to each other, and then this one is like spherical. Okay, so if we have like this kind of situation, the bond angles, we should be having like bond angles of 90 degrees. Okay, we should be having bond angles 90 degrees, but in the real situation, we having bond angles 120 degrees, and we also having bond angles 109.5. Okay, why? If we base on this s orbital and p orbital, the bond angle should be 90, but in the real situation, we having, okay, 120. Okay, and then we also having like 109.5. Okay, why? Because in the process of the chemical reaction, okay, reaction, okay, before they react, okay, before they react, they will hybridize first, okay, they will hybridize first. What it means by that is they will do this, okay, you see this one, okay, so this is 2s and 2p, okay, total, this is 4 orbitals, okay, 4 orbitals. So what they do is they will mix first, they will hybridize, okay, they will mix first before they react, okay. So example, sp hybridization, they will take this one s and one p, they will mix up together, okay. You see this one, different shape. After they mix, they become same shape, okay. So we start with 2, we end up with 2. 2 different shape, we end up with 2 same shape, okay. It depends on the situation. So we can have SP, SP2, SP3, okay. So in this case, we will choose, okay, 1s and 2p, okay. We take 3 different shape, okay. We mix, hybridize, okay. We mix into 3 orbital of the same shape, okay. And then for the sp3 hybridization, we take this one, okay, hold on. Yes. Okay, we take 4 different shape, okay, we mix it, okay, and then now we have 1, 2, 3, 4 same shape. Yeah, okay, so it works, okay, 3 same, 4 same, okay. So if we do not mix it, if we just have like what we start with, all the bond angles will be 90 degrees. But after we mix it, we can have this bond angle 180 degrees, which we have, 120 degrees, which we also have, and then this one 109.5, which we also have. Okay, so what is this hybridization? Okay, actually we don't really know what happened. It's just that in the real situation, we see this happening. So the hybridization is just a theory, okay, a theory we come up with to explain this. Okay, so we see all these molecules with different shape and different bond angle. How come they become like that? Okay, we use this hybridization concept to explain it. Okay, why it become like that. Okay, so here we have like some more example here. Okay, sp hybridization. um okay, if we have time later we can go through. Okay, now pi bonds. Okay, pi bonds, it happens for double bond. Okay, so you see just now we are saying that in IGCSE, the single bond and the double bond, we don't see any difference. Okay, but in the A levels we start to understand they are different. Okay, okay, so the single bond is just sigma bond only. Okay, sigma bond only. Okay, but when we have the double bond and triple bond with sigma bond, okay, plus pi bond. Okay, sigma bond plus pi bond. We just use the line to represent. They look the same, but they are not the same. Okay, so we'll see how they are different. Okay, so this pi bond is, okay, when we have sideway overlap. Sideway overlap. Okay, so what happened? Example, we have, okay. 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 Actually, we have this situation here. Yeah. Okay. We have this situation. Okay. The carbon. Uh, okay. So this one is a normal carbon. Okay. So it form a sigma bond here. Direct overlap, the carbon. Okay. 2p and 2p. Okay. So they form this sigma bond. Okay. What is actually happening? They are doing sp2 hybridization. Okay. They are doing sp2 hybridization. So basically, this carbon, um, the carbon, it has, okay, like this. Okay, carbon is 6 electron. 6 electron, 1s2, 2s2, 2p2. Okay, so 2s, 2p is like this. Okay, 2s, 2p. Okay, so now what is trying to do in the sp2 hybridization? Uh, okay, so let me go into a bit detail so it makes sense. Okay, so let's see. Okay, uh, this one. Okay, so at first it's like this. The carbon, uh, the electron configuration is like this, original. Okay, original like this. Okay, but after that, what is doing? It wants to hybridize. Okay, before it hybridize, it will okay, let me find another uh okay, before it hybridize, it will excite the electron. So this one, it will go to here. Okay, excite the electron. So basically, um one electron will come here, and then it will take, okay, these three. Okay, it will take these three. It will do the sp2 hybridization. It will do the sp2 hybridization. So this one, three different, okay, it turned to three same. Okay, it hybridized. Okay, so after it hybridized, it remain one. Okay, remain one of the p orbital is not hybridized. Okay, the one that is not hybridized is doing this pi bonding. Yeah, okay, it's doing this pi bonding. So this carbon, okay, it got the sigma bond here, and then it's got this, okay, unhybridized, okay? So they get quite close, they will overlap, okay? So when they overlap, they form this pi bond, okay? It looks like two pi bonds, but this is one pi bond, okay? It overlap up and down, but actually it's just one pi bond, okay? Yeah, so they overlap like this, okay? But normally we say that this is a weak bond, okay? This one, the overlap is a lot, large area of overlap. This is a strong bond. Okay, this one, it overlap just a bit of overlap. So this is a weak bond. Okay, so what we say, this double bond is actually made of one sigma bond, which is strong. Okay, and it made of one pi bond, which is weak. Okay, so that is the idea. Yeah. So before we think these two bonds, they are the same, but actually they are not the same. One sigma strong bond, one pi bond, weak bond. Okay. So this is quite useful to know because normally when this carbon bond, when it react, it is the weak bond that react. Okay. The strong bond, it stays there. Okay. So it gives us a little bit detail what is happening. Okay. Yeah. So this one is just talking about what is going on there. Okay. Yeah. So we have this sigma bond. Okay. The sp2 hybridization. Okay. It forms the sigma bond here and then the pi bond, the overlap. Okay. Yeah. So anything not clear, you just stop me. Okay. You just stop me. Yeah. So because of the sp2 hybridization, it got the bond angle of 120 degrees. Okay. And then another, yeah, so normally the weaker pi bond is the more reactive one. Okay. And then the double bond, because of this overlap, okay, it fixed this, okay, it fixed this CC. It cannot rotate easily, okay. It's fixed the position, but this single bond, it can rotate. The double bond, it cannot, okay, cannot rotate. Because of this pi bond, it fixed the position of the carbon. Okay. Yep. Okay. So how about when we have triple bond? Okay. So when we have triple bond, we are doing sp hybrid. Okay. Sp hybrid. What does that mean? Okay. Yeah. So this one. Okay. So for the triple bond, we have these four orbitals. We only take two. Okay. We only take two. For the hybridization, we have two unhybridized. These two unhybridized is the one that happen the overlap. Yeah, like this. Okay. We have two sets of overlap. Okay. So we have one sigma bond, two pi bond, one sigma bond, two pi bond. So that's why we have the triple bond. So that's how we get the triple bond. Okay. Yeah. Okay. Okay. Intermolecular forces. Okay. Okay, sigma and pi bond, shape of molecule, we already done. Okay, so now we'll look at the intermolecular forces. Okay, how it happened. Yeah. Okay, so for the covalent compound, we have intermolecular forces. Okay, why? Okay. Okay, so for the simple covalent molecule, we have this the covalent bond itself, which is very strong. Okay. And then we also have the bond that is between the molecules. The bonds that are between the molecules. So intermolecular force that is weak. Okay. So we have two types. Okay. Two types of bonds. Okay. So the actual covalent bond, which is strong, and then the one that is in between the molecules. Okay. In between the molecules, they are the weak intermolecular forces. Okay, so when we heat up these covalent molecules, like let's say we heat up water, okay, let's say we heat up water, we are not breaking this covalent bond. We are breaking the intermolecular forces. Okay, so when water is boiling, we are not breaking the covalent bond, we are breaking the intermolecular forces. Okay, so yeah. So because these weak intermolecular forces, they are weak, so that's why simple covalent molecules, they normally have low melting and boiling points. Okay, because we just need a little bit of molecules, I mean a little bit of energy to break this bond, so that's why they have low melting and boiling point. Okay, so this intermolecular forces, we have three types. Okay, permanent dipole forces, okay, instantaneous dipole forces, and hydrogen bonding. Okay, so we have three types. Okay, so now we'll look at what's the difference. Okay, permanent dipole forces. Okay, this is straightforward. Example, we have HCl. HCl, because this is a polar bond. Okay, so polar bond, we have the partial charge, partial positive charge and partial negative charge that is always there. Okay, this partial positive and partial negative charge, they are always there. That's why, okay, it can interact with the neighbor. So the neighbor, the delta negative here will interact with the delta positive of the neighbor. So they have attraction because of the delta negative charge and the delta positive charge. They have attraction. Okay. And then this attraction is because the this polar bond is always there. It's always there. So this dipole force, this is permanent. Okay. This dipole force is permanent because the polar bond is always there. Okay. So later we'll see instantaneous, that is temporary. Okay. The instantaneous is temporary. This one is permanent. Okay. Yeah. Because this polar bond is always there. This partial charge is always there. Okay. But this one, it compared to a typical covalent bond, is still quite weak, 100 times weaker. Okay. Compared to a real covalent bond, is still quite weak. Okay. So this only happen for polar molecules. Okay. So this only happen for polar molecules. Okay. Non-polar cannot. Okay. They must have this polar bond. Okay. It only happen for polar molecules. Okay. How about instantaneous dipole? Okay. Instantaneous dipole is happen all molecules. All molecules, whether it's polar or non-polar. Okay. Okay, I just want to quickly mention is that this class, actually I recorded it. Okay, I make a recording of this class. So later I will send you the link. Okay, so I record the class and then I upload to the YouTube as a unlisted. Okay, unlisted video, meaning only people with the link can see it. Okay, so I will share the link to you only, so you are the only one that can see it. So if you want to come back to like uh listen again, so let's say you forgot something I say or anything you want to recall, you can come back to watch the video later. So later I will send you the link. Okay, but at any time you got question, you just stop me. Okay, yeah, so coming back to here, this instantaneous dipole, it can happen for all molecules. So just now, this permanent dipole, it only happen for polar molecules. Okay, only happen for polar molecules. This instantaneous dipole is all molecules, polar or non-polar. Okay, why? it only got one condition. You just need to have electrons. Okay. So as long as you have electron, this instantaneous dipole can happen. Okay. All molecules, every molecules have electrons. So every molecules can have the instantaneous dipole. Okay. So yeah, it's there all the time. Okay. So how it happened. Okay. So how it happened. So although this instantaneous dipole, it can happen in all molecules, but we normally focus on the non-polar molecules. Okay. We normally focus on the non-polar molecules. The polar molecules, okay, so now I just quickly summary. Polar molecule, it can have permanent, okay, permanent dipole. Okay. It can also have instantaneous. Okay. Non-polar, okay, it can have instantaneous only. Okay, because it got no the polar bond. Okay. So polar molecules, it can have permanent dipole and instantaneous, but normally we focus on the permanent dipole because it is stronger. Okay. This one is weak. Okay. So the stronger one, like this one is almost, we don't feel it because it's too weak. So we focus on the permanent dipole for polar molecules. So for non-polar molecules, because it does not have the permanent dipole, so it only have the instantaneous dipole. So we will focus on this one. Okay. So polar molecule, it got both, but we focus on the permanent dipole, which is the stronger one. The instantaneous, because it's very weak, so we don't feel it very much. So we don't focus on it. Okay. So for non-polar, we'll focus on the instantaneous because that's the only one. Okay. So now let me just quickly show this table, the summary. Okay. So it gives us some information. Okay. Yes. Okay, so it's a little bit okay, hopefully you can see. So this one is instantaneous. Okay, it happens for all molecules. Okay, it's very weak. It's only 0.1 to 5 kilojoules. Okay, this dipolar forces, this is the permanent dipole. It happens for polar molecules only. It is stronger, 5 to 20 kilojoule per mole. Okay, hydrogen bonding, we'll look at this later, is stronger. Yeah, 5 to 50 kilojoules per mole. Okay, yeah. So, okay, so this hydrogen bonding is actually is also permanent dipole. It's just that it is a stronger type of permanent dipole. Okay, so it's special. Okay, yeah. Yeah. So this instantaneous dipole, we just say that it happened for all molecules. Okay. So it happened for all molecules. How it happened? Okay. As long as we have um electron, it can happen. Okay. So how it happened? Okay, let's take a look. Okay. Yeah. Feel free to like stop me anytime to ask question or to skip ahead. Okay. Now I explain how this instantaneous dipole happen. Okay. So we see here hydrogen, hydrogen. Okay. Hydrogen, hydrogen bond. This is non-polar. Okay. Non-polar. So non-polar, normally we say that if we got two hydrogen molecules, okay, normally we say there is no attraction because they don't have any like delta. They don't have any delta. Normally, we say that they have no attraction. Okay? Because electrons are evenly distributed. But in the real situation, Okay, so if we try to, like, let's say we measure it with some instrument, the real situation we measure, we find that they actually have attraction. They have attraction. Why? We predict they have no attraction because the electrons are just like evenly distributed. They are non-polar. We expect no attraction. But in the real situation, they have attraction. Why? Because the electrons, they are not always in the fixed position. The electron, they are moving all the time. They are moving all the time. So sometimes, sometimes they move slightly to one side. Okay, you see this one, they got two electrons. So these two electrons, normally they are evenly distributed, but they are moving all the time. Okay, so let's say out of 100 seconds, it got 2 seconds. It's unevenly distributed. So now it will give us a slightly negative charge here and then slightly positive charge here. Okay, so more electron density, less electron density. Okay, so it just happened like maybe in 2 seconds or 1 second or 0.5 second out of 100 seconds. So this is what we call instantaneous dipole. What it means by instantaneous is non-permanent. Non-permanent is temporary. Temporary. It's only once in a while, it just unevenly distributed. Okay, most of the time, 99 seconds is the even situation. So that's the difference with the permanent. The permanent is there all the time. This one instantaneous is only temporary. But this temporary is good enough. It's good enough because even for 2 seconds, it got the delta, it can have the attraction. Okay, it can have the attraction. So that's why in the real situation, we measure the attraction. Okay, because it can happen. Although not often, but it can happen. Okay, yeah. So we are saying that as long as there are electrons, this instantaneous dipole can happen. Electron much more mobile. Okay, so it will give a fluctuating dipole, instantaneous dipole. Okay, the dipole that can happen only very short time. Okay, and then this is the step one. Step one. Okay, step two. What does it do? Yeah, okay. So what does it do? Okay, let's take a look. Okay. So at first, it's evenly distributed. And then sometimes, okay, like 1 or 2% of the time, you got the instantaneous dipole, uneven distribution. Okay. This instantaneous dipole, okay, let's say it got the neighbor that's next to it. It will induce a dipole in a second atom. Yeah, okay. So let's say we have the HH. Okay. So this one, it got the instantaneous dipole. This one, it doing nothing. This one doing nothing. It just stay next to it. Then it got influence. Okay. So that's what we call induced dipole. So two things can happen. Instantaneous dipole happen and then it induced the dipole in a second atom. So this one is also temporary. Yeah. Okay. So now they can have the attraction. Okay. So we see this one it only happen 1% of the time or 2% or even 0.5%. Okay. It's not very often. So that's why we know that it's very weak. Yeah. Okay. This permanent dipole is there all the time. Like HCl, the permanent dipole is there all the time. So it's stronger. Okay. Yeah. Okay. So it will induce a corresponding dipole in a nearby molecule. Attraction between the molecules is called instantaneous dipole, induced dipole force. Okay, so that's what we mentioned here. Okay, ID. Okay, permanent dipole, instantaneous dipole, induced dipole. Okay, so that's what we're talking about here. Okay, yeah. Okay, so we have another name for it. Okay, another name for it. Okay, temporary dipole, induced dipole, or London dispersion force. Okay, so another point about this is that the strength of attraction it decreases rapidly with the distance. Okay, uh, yeah. So this one, okay, when they are close together, is it can happen, but when they are far away, it's much weaker. Okay, so the distance is very important. Okay, yeah. So now we are looking at a few key points about this induced dipole. Okay, so first we need to think about the distance. Yeah, okay. So first point, we need to think about the distance. Okay, hold on. Okay, first point is distance. They need to be close together. Okay, so it's a very short range force. When they are far away, it cannot happen. Okay, another one, it depends on the number of electrons within the molecule. Okay, so the more molecules, the stronger. So let's say we compare HH and Cl. Okay, so Cl, they have more electrons. Okay, because chlorine is 17 and 17. Hydrogen is 1, 1. Okay, so this one is less electron. Okay, so okay, less electron. So let's say the distortion is like this. Okay, it's a small distortion of the electron cloud. Okay, but for the chlorine, it can be a large distortion. Okay, because it got more electrons. So the delta is stronger. Okay, the delta is stronger. Okay, so that's the idea. More electrons, the instantaneous dipole will be stronger. Okay. Yeah. More electrons, a larger chance of instantaneous dipole, and the larger the dipole is likely to be. Okay, and then it also depends on the shape of the molecule, because some molecules they have greater area of close contact, the larger the force. Okay, induced dipole also occurs whether or not they have permanent dipole. So whether or not they have hydrogen bond, they don't care. Okay, all molecules will have this instantaneous dipole, all. Okay, as long as they have electrons. Okay, so now we will look at some examples. These two, okay, you see this one, boiling point is higher. Higher boiling point means higher strength. Okay, so this one is stronger. Higher boiling point. This one is a stronger instantaneous dipole. Why? Because silicon, it got more electron compared to carbon. Okay. Another example. Okay, fluorine, chlorine, bromine. Again, the boiling point is increasing, means it becomes stronger. The instantaneous dipole is stronger. Why? Because when we're going down the group, more electrons. Yeah, okay. And then this one, okay. So this one is a carbon chain. Okay. Okay. So this one is carbon chain. Okay. So we can see longer carbon chain. They have more electrons. So we can see again the boiling point increase. They have stronger um instantaneous dipole, induced dipole. Okay. And then the final comparison. Okay, we have this one. Okay, this one, they have the same number of electron. Okay, so C4, H, okay, no, C5, H12. This one also C5, H12. They have the same number of electron. Why this one is higher boiling point? Why? Because this one is spherical. Okay, spherical like this. Okay, this one is cylindrical. Okay, this is cylindrical, the shape. Okay, so this one is more contact area. Okay, more contact area, stronger instantaneous dipole. Yeah, okay. Sausage shape, area of close contact is greater. So the ID is stronger. So it got higher boiling point. Okay, next, hydrogen bonding. Okay, hydrogen bonding. So hydrogen bonding is also permanent dipole. Okay, it's also permanent dipole. It's happened between, okay, hydrogen, nitrogen, hydrogen, oxygen, hydrogen, fluorine. Okay, we still have the delta, the partial charge. We still have the partial charge, but this one is stronger. Okay, stronger than the permanent dipole. Why? Hydrogen atom, it got one s electron. Okay, and then it's at the pi bonding. Okay, so nitrogen, oxygen, fluorine is electronegative, highly electronegative. So we have the delta positive on the hydrogen. Okay, so it got the delta positive charge. Okay, the positive charge is even greater when the hydrogen is bonded to electronegative atom like nitrogen, oxygen, or fluorine. Okay, so the highly delta positive hydrogen, it got a particularly strong attraction from a lone pair of electrons on the adjacent molecule. Okay, so this intermolecular forces is very strong. We call it hydrogen bond. Okay, it's roughly 10 times stronger than the dipole-dipole, okay, or the instantaneous dipole, but it's about 10 times weaker than a typical covalent bond, okay? Compared to a typical covalent bond, it's still weaker, okay? So what does it look like, okay? So we can see here, hydrogen bonded to nitrogen. This is the hydrogen bonding, okay? This is the hydrogen bonding, okay? Because it's bonded to a nitrogen, this is a strong delta positive, a strong delta positive, so it can interact with the delta negative on the nitrogen. So that is the hydrogen bonding, okay? So this is the hydrogen bonding. So it got some effects, okay? This hydrogen bonding, it got some effect. So it makes the boiling point of ammonia, water, and HF, they are higher than normal, okay? So we see here, okay? So, okay, methane is here. Okay. So NH3, maybe it should be like this. Okay. Maybe the trend should be like this, but they are much higher. Okay. Because of the hydrogen bonding. Okay. And then they are also higher than other hydrides. Okay. So it's unusually high boiling point. Okay. Unusually high boiling point. Okay. And then this hydrogen bond, it also happen for the protein folding. Okay, so you will learn in the biology, in the protein synthesis, one of the steps is the formation of the hydrogen bonding. Okay, so we can see that this hydrogen bonding is very important for the biological systems. Okay, so it appears a lot in living things. Okay, like the DNA, nucleic acid, we also have hydrogen bonding. Yeah, okay. And then another example is alcohol. Okay, so if we compare alcohol to alkane, normally alcohol, although they have the same number of electrons, but they still have a higher boiling point. It's because of the hydrogen bonding. Okay, yeah. Okay, you see? So they are higher than usual, their boiling point, okay, compared to the methane. Yeah, okay. So example, so this one in the DNA, okay? Hydrogen bonding in the DNA, which is very important, okay? Okay, so this one compare alkane and alcohol. Yeah, okay? Same number of electron, but this one higher boiling point. Higher boiling point because of the hydrogen bonding. Same here. Okay. Higher boiling point because of the hydrogen bonding. That can happen in the alcohol, but not in the alkane. Okay. Yep. Okay, so basically it's done for this part. Okay, let's take a quick look at this example. It will help us to understand. Okay, so we got three molecules here. Okay, which one will have the lowest boiling point? Which one will have the highest? Okay, so this one is mostly, we can say this is non-polar. Okay, this mostly non-polar because carbon and hydrogen is very similar, the electronegativity. Okay, so we can say this is mostly non-polar. So this one will be instantaneous only. Okay, so this one we see we have the CCl bond. Okay, and we also have the OH. Okay, so this one we will have the permanent dipole, and we also have the hydrogen bonding. Okay, and then this one we have the CCl. Okay, so this one we have the permanent dipole only. Okay, so straight away we can see this one will be the lowest boiling point because it only got the instantaneous. Okay, so A will be the least intermolecular attraction, so it will be the lowest boiling point. Okay, so A is the induced dipole only. Okay, okay, B will have the highest. Why? Because it got the permanent dipole and also the hydrogen bonding. Okay, B will be highest, dipole and hydrogen bonding. So C will be the permanent dipole only. Okay, so C is in between. Okay, so that's the idea. Okay, cool. So this is done. Okay, now so this intermolecular forces is done, and this hydrogen bonding is done. Okay, next solid and liquid state of matter. Okay, so this one is unit 4. Okay, so unit 4 here. Okay, hold on. Yeah. Okay, so this one is also quite a big topic. Okay, let's try to go through as quickly as possible. Okay, three state of matter. Okay, no problem. Heating curve. Okay, so I think this one you are familiar. No problem. Okay, heating curve, and then solid, liquid, gases, the characteristics. Okay, so touching one another, fixed, regular, 3D, vibrate about fixed position, liquid moving randomly to the liquid, vibration, rotation, translation. Okay, gas far apart and so on. Okay, so now we're looking at the lattice. Okay, different kind of lattice, non-crystalline and crystalline. Okay, yeah. Okay, so for the crystalline one, we have the unit cell. Okay, it's a regular arrangement. Building blocks of lattice. Okay, so we have different type of lattice. Okay, we have different kind of lattice. Okay, simple molecular lattice like ice, giant molecular lattice like silicon dioxide or diamond or graphite, ionic lattice, as in the ionic compound. Okay, simple molecular lattice, okay, is example, okay, okay, is made of simple covalent molecules, okay, so no chemical bonding, okay, no chemical bonding. It's just based on dipole, instantaneous dipole, and hydrogen bonding. It's quite weak, okay, yep. So example, this one. So hydrogen chloride. So this one is intermolecular forces. Okay. So it's quite weak. Okay. So even if it turns to solid, like ice, okay, it got the hydrogen bonding, it's still quite weak. Okay. Yeah. Okay, so I will go quite quickly. Yeah. Okay. Yeah. So this one is water. So water, hydrogen bonding, when it turns to ice, it still form a lattice. Okay. Giant molecular lattice. So this one we are quite familiar, like diamond, silicon dioxide. Okay. Giant covalent lattice. They have high melting point because this is like 100% covalent bond. 100% covalent strong bonds. Okay. So they are very strong. Electrical insulator. Okay. So they don't have free electrons. Hard, strong, and non-malleable. Okay. Very strong. Okay. Um, okay. Ionic bonding. So ionic bonding, they form ions. So these ions, they attract strongly together. So they will form. Yeah. So just now, you see here, just now the electronegativity. Okay. So this one, same electronegativity. This is non-polar. Okay. So this one, we have a difference in electronegativity. So this one is covalent. Okay. Polar covalent. You see, this one, the electronegativity difference is 3. It's very large. So when we have a large difference in electronegativity, we form ionic compound. Yeah. Okay. So ionic compound, they will form lattice. Yeah. Okay. So they will form lattice like this. Okay. Ammonium ion, okay, also can form the lattice. Okay. Carbonate ions. Okay. Sulfate ions. Okay. Ionic valency table. So we just need to know the charge on the ions. Okay. So we just need to memorize, okay, some of them. Yep. Okay. So with that, okay, we can work out the um formula. Example, zinc nitrate. Zinc is 2 plus. Zinc is 2 plus. Okay. Nitrate is -1. So we need 2 of them. Okay. To balance the 2 plus. So zinc is 1 zinc, 2 nitrate. Okay. Ionic lattices. Okay. So ionic lattices. Okay. So it can form the lattice with different coordination number. It will depend on the size of the ions. Okay. And the charge. So some example. Okay. Yeah. So we can have um coordination number will depend on the size of the ions. Okay. And the radius. Okay. Yeah. Okay. Okay. Ion polarization and charge density. Okay. Yes. Okay. So we will find that some ionic bonds, they have small degree of covalent character. Okay. Small degree of covalent character. Okay. Because polarization of the negative ion by the positive ion, it occurs to be the greatest extent when small highly charged cation is bonded to large anion. Okay, outer electron around the large anion, not firmly held by the nucleus, can be attracted by the strong electric field around the small, highly charged cation. Increased electron density between the two ions, a degree of localized covalent bonding. Okay, so this one is not too important. Okay, okay, properties of ionic compound. Okay, so they have strong electrostatic attraction between the oppositely charged ions. Oh, I just realized we almost 6 o'clock. So just now we start at 4 p.m. Okay, so we will finish around 6 p.m. Okay, so I think we can finish all the notes and then later at the 8 p.m. Okay, later we can discuss. Okay, so our plan. Okay, Okay, let's see how much we have. Yeah. Okay, so this one we are quite familiar. Okay. Ionic compound, metallic bonding, we are also very familiar, no problem. Graphite, okay. Yeah, okay, this is fine. And then this is about gas. So we don't need to know about gas for now, right? Just solid and liquid. Gas, not yet. Okay. So let us quickly discuss our schedule before we go. Okay. Hold on. Okay. Wait. Okay. Hold on. Okay. Okay. This is our plan as I discussed with your dad today. Okay. 4 to 6 p.m. Okay. And then 8 to 10 p.m. Okay. Tomorrow is 4 to 6 p.m. only. Okay. Wednesday, 10 to 12. Okay. 10 a.m. to 12 noon. Okay. And then 2. Okay. 2 to 4 p.m. Okay. So this is our schedule so far. It's total 10 hours of class. 10 hours of class that we plan for. Okay, but this one is very flexible. Okay, very flexible. So you can change anytime. So as long as I can make it like we can change, no problem. So we just done the first one. So the rest, okay, it's flexible. Okay, so you want more, you want less, we can discuss. And yeah, so because I send you the questions, yeah, so I send you the question is a lot. So these questions, I think, is quite good because these are real past exam questions. So you can see here, they mention which year, which paper. Okay, so these are real past exam questions start from 2002 until 2023. Okay, so this is quite good. So we can practice on the real past exam paper. So just now I sent to you the paper one, which is the multiple choice, and the paper two, which is the theory paper. So yeah, we can go through together. Okay. So on this topic, um, yeah. So basically, depends on you. Start from the next class. We can go through more theory if you want, or we can go straight to the questions in the next class. And for the questions, if you want to try by yourself first, then maybe tonight we don't have a class if you want to try by yourself the question. But if you want me to like go through, straight away go through, then we can continue at 8 p.m., something like that. So the rest of the time, we just going through the questions. Yeah, so basically like that, the plan. But if you have other like ideas, you want to do other things, you just let me know. Okay? Yeah. So what do you think? We continue at 8 p.m. or you just want to like rest or do the questions by yourself and then we can do it tomorrow, 4 to 6. What do you think?
We can do it later.
Okay, so we continue at 8 p.m. tomorrow, yeah? And then sorry, later we start again at 8 p.m. And then so you just want to like get started with the questions or anything else you want to do in terms of the theory?
I think we can do the questions, try the questions for now.
Yeah. Okay. So later 8 o'clock, we will get started with the questions. Okay, so I recommend we start from the end. Okay, we start from the end, which is the 2023 one, because it's more closer to the syllabus. Okay, so this one, the 2002 one, is still like okay, is still like useful, but the most useful one is the recent one, 2023, 2022, and so on. Okay, so we start from the end. Okay, so if you want to try by yourself, I recommend you start from the end also. Okay, and the paper 2 also. Yeah, we start from the end. Depend how much time we have, we will go through. We try to go as far as possible. Okay, yeah. So that's the plan for now. Okay, so we will stop now. It's 6 o'clock. So we will start again at 8 o'clock. Okay, so I will see you later.
Uh,
Okay, bye bye, bye bye, bye bye.